Tamu Massif is a massive underwater volcano located in the Pacific Ocean, about 1,000 miles (1,600 kilometers) east of Japan. It's one of the largest volcanoes on Earth and holds several remarkable distinctions. Tamu Massif covers an area of approximately 120,000 square miles, 310,000 square kilometers, roughly the size of New Mexico. Its peak rises about 13,000 feet, 4,000 meters, above the surrounding seafloor, though it remains about 6,500 feet, 2,000 meters, below the ocean surface. The volcano formed around 145 million years ago during the late Jurassic to early Cretaceous periods. It's located at the junction of three tectonic ridges in the Shatsky Rise, an underwater mountain range. Scientists believe it formed through massive lava flows that spread over vast distances along the seafloor. Tamu Massif was first mapped in the 1990s, but its true massive scale wasn't fully understood until 2013 when researchers from Texas A&M University, hence, Tamu, confirmed its size through detailed seismic analysis. The name, massif, refers to a large mountain mass or compact group of connected mountains. What makes Tamu Massif particularly interesting is that it appears to be a single volcano rather than a complex of multiple volcanoes. This makes it potentially the largest single volcano on Earth by area, though it's much less tall than shield volcanoes like Mauna Loa in Hawaii. The volcano has been dormant for millions of years and shows no signs of current activity. The discovery of Tamu Massif has helped scientists better understand how massive underwater volcanic systems form and the role they play in ocean floor geology. William Sager, the same scientist who originally declared it the world's largest volcano, led new research that analyzed magnetic field data over Tamu Massif using 4.6 million magnetic field readings collected over 54 years along 72,000 kilometers of ship tracks. The magnetic anomaly patterns they found were unexpected for a shield volcano. A huge shield volcano should not form magnetic stripes. Sager explained, if it formed in a short time, one polarity period, it will have a coherent overall anomaly. If it formed during multiple polarity periods, the anomaly should be irregular. Lava flows that travel long distances should destroy the magnetic stripes. The magnetic data revealed that Tamu Massif formed through extraordinary mid-ocean ridge crustal formation rather than typical volcanic eruptions from a central point. This makes it a unique hybrid of oceanic plateau formation and volcanic activity, something scientists hadn't seen before. A 2022 study using high-resolution bathymetry mapping revealed that Tamu Massif is actually segmented by several shallow valleys that divide it into 5 smaller mountains, each forming at a jumping triple junction. This segmentation pattern supports the theory that it was built through a series of ridge-centered eruptions rather than one massive volcanic event. As a result of these findings, Mauna Loa in Hawaii has reclaimed its title as the world's largest single volcano. Sager himself noted that the largest volcano in the world is really the mid-ocean ridge system, which stretches about 65,000 kilometers around the world, like stitches on a baseball. The Tamu Massif discovery has broader implications for understanding oceanic plateau formation worldwide. Scientists are now re-examining other large underwater volcanic features to determine if they form through similar processes. This research continues to reshape our understanding of how the largest volcanic features on Earth actually form, demonstrating how scientific understanding evolves as new data becomes available. The case of Tamu Massif perfectly illustrates how scientific discovery is an ongoing process of questioning, testing, and refining our understanding of natural phenomena. The formation of Tamu Massif and the broader Shatsky Rise involves intricate plate tectonic processes that scientists are still unraveling. Tamu Massif was created approximately 140 to 150 million years ago at the Pacifica-Zanagi-Farallon Ridge triple junction, which was one of 3 triple junctions operating in close proximity as the nascent Pacific plate began to expand. The tectonic setting was extraordinarily complex. The eruption coincided with an 800 kilometers, 500-mile, 9-stage jump in the location of the triple junction and a configuration change from ridge to ridge transform. Tamu Massif apparently formed along a segment of Pacific Farallon spreading ridge that rotated by 90 degrees as a triple junction migrated through the edifice. The 2009 Integrated Ocean Drilling Program Expedition 324 provided unprecedented insights into Tamu Massif's internal structure. The expedition cored Shatsky Rise at 5 sites, with penetrations ranging from 191.8 to 324.1 meters, recovering 52.6 to 172.7 meters of igneous basement at 4 sites. The drilling revealed remarkable volcanic characteristics. Site U1347 cored a 160-meter igneous section of alternating massive flows and pillow lavas on the eastern upper flank of the volcano, with massive flows as thick as 23 meters. These massive flows are associated with volcanic eruptions at higher fusion rates and are similar to characteristics of flood basalt provinces. The scale of individual lava flows is extraordinary. IODP Expedition 324 cored into an approximately 160-meter section of volcanic lavas, dominated by thick, 8 to 23-meter, massive basalt flows at the top and the base of the hole, with a middle part composed of alternating numerous pillow basalt inflation units and thin, less than 1 to 2 meter, massive flows. These massive flows provide crucial evidence about eruption style. Massive flows are thickest and make up the largest percentage of section on the largest and oldest volcano, late Jurassic Age Tamu Massif. Thus, it may have formed at higher fusion rates. Such massive flows are characteristic of flood basalts, and similar flows were cored at Ontong Java Plateau. Recent research suggests the formation mechanism is more nuanced than originally thought. Recent investigations initially envisaged a competition between two end-member models, the thermal plume head and the fertile mantle melting beneath plate extension. Both hypotheses find support from new data and interpretations, but both do not fit some data. Thermodynamic modeling of magmatism at Shatsky Rise now suggests that neither mechanism is adequate on its own, and in fact plume-ridge interaction is required to explain the formation of this ocean plateau. The most recent comprehensive magnetic surveys have revealed the entire Shatsky Rise's formation history. All of Shatsky Rise is traversed by linear, curvilinear magnetic anomalies, indicating its formation by enhanced ridge volcanism. The pervasive occurrence of linear magnetic anomalies within Shatsky Rise implies that these volcanic edifices must have formed by spreading analogous to mid-ocean ridges that formed anomalously thick crust. Analysis of rock samples shows unique characteristics. Basaltic glasses from Site U1347 are evolved Thol IITIC basalts containing 5.2-6.8 Wt% MgO, and are principally located within the compositional field of mid-ocean ridge basalts, but with systematically higher FeO, lower Al2O3, CO2, and sodium oxide concentrations. Fractionation-corrected values indicate more than 20% partial melting of the mantle during the generation of the parental magmas of Tamu Massif. Scientists have calculated impressive eruption rates. Using age constraints and magnetic anomaly patterns, researchers estimate that 2 × 10⁶ km³ of material erupted at a minimum rate of 1.7 cubic kilometers per year, representing a massive eruption consistent with the plume head hypothesis. Today, Tamu Massif represents a unique geological feature that challenges traditional volcanic classification. It appears to be a hybrid between typical volcanic construction and ridge spreading processes, formed through extraordinary circumstances involving multiple interacting plate boundaries, possible mantle plume activity, and complex tectonic reorganization during the late Jurassic period. This makes it not just remarkable for its size, but also for the insights it provides into how the largest volcanic features on Earth actually form. Thanks for watching. Like and subscribe, and don't forget to explore more geological wonders on our channel.